Lesson number 25, Daily Summary. In this lesson, we tackle some word problems that lead to quadratic equations. A farmer has a rectangular garden plot surrounded by 200 feet of fence. Find the length and width of the garden if its area is 2,400 square feet. In this problem, we will make use of the semi-perimeter. Okay, so first of all, we need to define some variables. The question is asking for the length and the width, so it feels like those are what our two variables should represent. So we'll let L equal the length, but remember, it's not enough to just have a quantity word. We also want a unit word. Square feet tells me that feet is the correct unit word for length. So L is the length of the rectangle in feet. W is the width of the rectangle in feet. Please don't write just W equals width. You need to have a unit included. Okay, so we draw a picture. There's our generic looking rectangle over there labeled with L's and W's. Now we're going to make use of the fact that the garden plot is surrounded by 200 feet of fencing. So what does that mean? It means we use 200 feet of fencing all around this rectangle. And so that means if we add up all of the sides going all the way around the rectangle, we should get 200 using all of that available fence. So if you add L plus W plus another L plus another W, you had better get 200. And we can combine terms here. That's really 2L plus 2W equals 200. And you might have already thought of the perimeter of this rectangle, and that's cool because 2L plus 2W is exactly the perimeter. So for sure, using the perimeter equal to 200 is a good technique here. And it turns out that equation is fine in its current form, but it's much easier to make use of something called the semi-perimeter. And semi oftentimes means half. And so we are going to do half of the perimeter, which means taking this entire equation and dividing both sides by 2. So if I do half of the right-hand side, I just get 100. And then half of the left-hand side I can split. So I'm going to write this and then I'll erase it. But 2L plus 2W, half of that thing, right, divide it by 2. And I know I can split that into 2 fractions, both of them over this denominator. And then I can reduce. 2's cancel, 2's cancel. And we just get L plus W on the left-hand side. Okay, so L plus W equals 100 is a friendlier version than the perimeter equation. And now we're going to use the other part of this problem that's given, which is that we want the area to be 2,400 square feet. So I don't yet have a formula for the area on this page, so it feels like I should write a formula for the area right now. So let's put that right here. Area equals, so the area of any rectangle is length times width. And we're told in this case that the area of this particular rectangle is 2,400 square feet. So there is our formula. And we're interested in finding a length and a width that satisfy the 2 equations we've got written out here. One of them is the L plus W equals 100, and the other one is 2,400 equals L times W. You could use trial and error, but and you'll get away with it in this particular case because the final answer here, the values of L and W are both nice numbers, integers. But this is an algebra course, so let's use some algebra even if you can just kind of guess and check your way to the right answer. So the algebra that we're going to do is similar to the algebra that we did a while back. I'll just make up some equations here. X plus y equals 5, 3x minus 2y equals 8. We had a couple of techniques for solving systems of equations just like this one. One of them was called the substitution method. The other one was called the elimination method. For example, if I wanted to get rid of the y's here, I would first multiply this top equation by 2, both sides. And when I do that, I would get 2y after I distribute that 2, and then I could add that 2y to this negative 2y, and the y's would all cancel. And I'd be left with just a simple equation with x's in it, in which I could solve for x. So that was called the elimination method, or maybe the addition-subtraction method. Another technique was the substitution method, and that would be where we solved one equation for one letter. For example, solve this first equation for x by subtracting y from both sides, and then we substitute what we just found into the other equation. So it's 3 somethings minus 2y equals 8, and where I said something, it was really x, but we're replacing x now with 5 minus y. So that was the first couple of steps of our substitution method. And this is great because this last equation we just wrote has only y's in it, and it's really easy to solve. Distribute the 3 and then combine like terms and then isolate the y. And so we had two techniques for solving this kind of system of equations, the elimination method and the substitution method. It turns out substitution is very general, and we're going to use that substitution same method over here with the equations we have on the right-hand side, the orange equation and the black equation at the middle bottom here. So let's use the substitution method, which again means solve one equation for one variable. Got lots of choices. Solve this equation for L, or solve it for W, or solve this equation for L, or for W. I'm going to do this equation because if I did this equation for L, for example, I could divide both sides by W, which is fine. But then I've got fractions throughout, and I'd rather avoid that if I can. So I'm going to solve this equation right here for L. Could solve for W, it doesn't matter. So let's solve that top equation there, this orange equation for L, by subtracting W from both sides. And then we are going to substitute that into the other equation right here. Instead of this L, we get to put 100 minus W. So the black equation now becomes 2400 equals something times W. And the something is supposed to be L, but as we saw up there in orange, L is the same as 100 minus W. So there is the substitution step. And this equation is better than any of the ones that were above because this equation has only one variable in it instead of two. And so let's go ahead and get this thing into a more standard form. 2400 equals, so let's distribute that W. So we go 100W minus W squared. All right, so now it's starting to really look familiar. I've got a W squared in my equation. Usually that means I want one side of the equation to equal 0. So let's make one side of the equation equal to 0 by subtracting the 2400 from both sides. So I'm going to put the minus 2400 last. I like my W squared to be first, so I'm just going to shuffle the W squared to the front. It's still minus W squared. I haven't moved it. I've just moved it. I haven't moved it to the other side of the equation. I've just shuffled it to the front. And then the 100W was really positive 100W, so it's still positive 100W. Just that this is in our standard order with the squared term first, then the first power term, and then the constant term. Okay, and then you solve that equation by either factoring, maybe greatest common factor first, but it's just 1, maybe a difference of 2 squares factoring, but it's 3 terms, or a 2 by 2 box factoring, which this one will work. So you could either do the 2 by 2 box, or you could do the quadratic formula. Either way is okay. And so I'll go ahead and do the 2 by 2 box method here real quick. With many details glossed over, but speed 2 by 2 box. Negative W squared, sum is 100W. Negative 2400 goes here. Product of that diagonal is positive 2400. W squared. And now the hard part, find two things that multiply to 2400 W squared and add up to 100 W. There are a ton of factors of 2400. I'm just going to jump to the answer here, but the answer in this case is 40W and 60W. Right? They multiply to 2400 and add up to 100. Multiply to 2400 W squared and add up to 100 W. So we'll put them in the box. I really glossed over that step. It would, in theory, take a bunch of trial and error to find the two things that work. And instead of factoring, you'd be welcome to use the quadratic formula in this case if you wish. And here we'll continue. The greatest common factor in the first row is W. Up here, we therefore need a minus W, and then a plus 60 to get that 60W, and then a minus 40. Careful there, because you already had a minus W at the top. So we need another minus sign to make it positive 40. So let's write our equation now. So this becomes 0 equals, so then we have our two factors from outside the parentheses, W minus 40 and negative W plus 60. And then we write the two simpler equations, 0 equals W minus 40 or negative W plus 60. And then we solve these equations for W, so we'll add 40 to both sides here. In the other equation, I like to add W to both sides. That way you get positive W. And we get W equals 40 and W equals 60. Mind you, this is not the length and the width of a single rectangle. This is two different widths of two different rectangles, and we still need to find the corresponding values of the lengths. So we did have a formula where we had L by itself. It's in the top right of this screen. L equals 100 minus W. So let's copy that down here at the bottom. L equals 100 minus W. So in the first case, if W is 40, then L is 100 minus 40, or 60. And in the second case, if W is 60, then L is 100 minus that 60, which is 40. And so we get two rectangles. One of them is a 40 by 60, and the other rectangle is a 60 by 40. In theory, two different rectangles, but in practice, there's only one 40 by 60 rectangle. So we actually ended up getting the same rectangle twice, but sometimes you really get two different rectangles, two completely different rectangles. Okay, on the next page is a reference sheet for you that just details the process that you can use to solve word problems that lead to quadratic equations. I'm not going to read through it, but I think you should pause the video here and read through this process. And when you're ready, we're going to move on to number 3 together. This problem involves a baseball being thrown. Here's the setup. The formula for the height of a baseball thrown into the air is h equals negative 16t squared plus 64t plus 4, where h is the baseball's height in feet and t is time in seconds since it was thrown. Let's use that equation to complete the table of values. Okay, so first we'll plug in t equals 0. So if we plug in t equals 0, for both of those t's, you get negative 16 times 0 squared plus 64 times 0 plus 4. And 0 squared is nothing, times negative 16, still nothing. 64 times 0, more nothing. Altogether, we just get 4, and that's it. And what that means is that 0 seconds into this experiment, meaning like the moment this ball is being thrown into the air, but it's like still like right there in your hand, about to leave your hand, the ball is 4 feet off of the ground. Okay, let's plug in t equals 1. Negative 16 times 1 squared plus 64 times 1 plus 4. So let's see, that's negative 16. Subtract that from 68. Can I do this without messing up 52? Sound okay? I think it's 52. Okay, let's plug in 2 for all of the t's. Negative 16 times 2 squared plus 64 times 2 plus 4. Okay, let's see. 2 squared is 4 times negative 16 is negative 64 plus 128. So that's positive 64 plus another 4, 68. Okay, go ahead and pause the video here and fill in the other two blanks for t equals 3 and 4, and then come back. And coincidentally, hopefully you discovered that the other two blanks are 52 feet and 4 feet, copies of the 0 and 1 heights. On the grid at right, graph the height of the baseball versus time by plotting points from your table above and connecting the points with a smooth curve. Let's give it a shot. So 0, 4, so we have to estimate 4 is just a little bit under the halfway here. 1, 52, again estimating where 52 is, maybe there. 2, 68, estimate 68. And then 3, we're back to the same 52, and then 4, we're back to the same 4. And then we connect with a smooth curve. We know this is going to be a parabola. It's got that t squared in it, and this is a downwards opening parabola because of the negative in front of the t squared. Okay, let's write the coordinates of the highest point. Well, it sure looks like the highest point is up there at 2, 68. Now, I think we can't really know for sure that that's the highest point, right? Like it's the highest point we plotted, but maybe this parabola happens to go like up and then like a little bit higher and then it comes back down, right? Like maybe the highest point goes through 268, but actually at 2.5, it's even higher. So we don't know for sure without finding the vertex per se. We'll be getting there. But the fact is, it is the highest point because of this symmetry, the 52s being equal to each other. That means the highest point has to be smack dab in the middle of the 1 and the 3. So the highest point has to happen at t equals 2. but we just kind of got lucky here. Okay, baseball reaches its maximum height at how many seconds? 2 seconds, that's the 2. And the maximum height of the baseball is how many feet? 68 feet. All right, number 4 kind of generalizes what we just saw with this particular baseball equation. If an object is thrown into the air from a height of h sub 0 above the ground with an initial velocity v sub 0, then its height t seconds later is given by this crazy looking formula. So first of all, the 0 in h sub 0 and v sub 0 are supposed to represent an initial something. H sub 0 is an initial height. V sub 0 is an initial velocity. And we use 0 to represent initial because you're imagining you do this experiment with a stopwatch in your hand. And the moment you release this ball, you start the stopwatch. But at that moment, like right before you've started the stopwatch reads all zeros. And so that's the 0 subscript that we're putting here. So here's the general formula. It says the height of the baseball is given by 1/2 times g, we haven't seen g yet, times t squared, okay, plus initial velocity times time plus initial height, where g is the acceleration due to gravity on Earth. G is a constant. It's probably just about anywhere you are, g is a constant, but the particular constant g is here on Earth is negative 32 feet per second, or negative 32 feet per second squared. If you're on the moon, gravity is not as strong, and the gravity on the moon would be a number closer to 0 than this negative 32 number. So the baseball formula was a special case of the formula above. For the baseball formula, we had this negative 16t squared plus 64t. So that 64 is supposed to represent the initial velocity. It's the number touching t. That's always the initial velocity. So apparently the baseball problem, in that problem, the baseball was thrown with an initial velocity of 64 feet per second from a height, an initial height, of 4 feet off the ground. Hey, that jives with what we found, right? When we plugged 0 in for t, we found the initial height was exactly 4 feet. And then where did this funny negative 16 come from? We'll take a look at the formula. It says you do half of g, always half of g. And on Earth, g is negative 32. So if you do half of that number, you get negative 16. And so every one of these kinds of problems you do here on Earth is going to start with a negative 16 t squared. Okay, so number 5, let's see if we can apply this formula in a slightly different context. A tennis ball is thrown into the air with an initial velocity of 25 feet per second from a height of 8 feet. Write a formula that gives the height of the tennis ball at time t, hint the formula that we saw up above. Okay, let's start identifying things. This 25 feet per second is the initial velocity in our formula that is symbolized v sub 0. The 8 feet is the initial height in our formula that's symbolized by h sub 0. And then I think we get to just copy the formulas. Here it goes. H equals 1/2. G on Earth is negative 32 times t squared. That's just copied. All the t's are just copied. Plus initial velocity, we said that was 25, times the t, that t is copied, plus the initial height, that's 8. The last thing we need to do is just multiply the half by the negative 32. Not at all surprised to again get that negative 16. And that right there is our formula, which tells us the height of this particular tennis ball at any moment in time after we throw it. Now, mind you, this formula breaks down once the ball hits the ground, right? Like we drew our parabola up here for this other problem. The parabola itself goes under the t-axis, right? But the ball cannot have a negative height. So the formula breaks down once you hit the ground.